Hey, what's up, everybody? Are you ready for some more statistics? Are you actually ready for some more probability in section 11.9 here? And I hope the answer is yes as we start to talk about binomial distributions. And we'll go over this entire title before the lesson's over. Binomial makes me think of the number 2, so there's going to be something with two options or two outcomes involved. And the distributions part I'll explain when we talk about what it means to have a probability distribution. A little joke to get started as you're getting your stat packet ready on page 16 for these examples. How would a bunch of astronomers organize a party? Well, it's simple, everybody. They would plan it. Check out this exploration and see if it reminds you of the probability topics that we had gone over earlier in the unit. It says, let's say we roll a die 5 times, find the probability. Okay, so we got to think back to how we would have done this. With a theoretical probability of getting no 3s when you roll a die 5 times. I also want to mention why this setup is actually binomial. When you roll a die, do you consider it just having 2 possible outcomes? Because I don't, right? You could get a 1, 2, 3, 4, 5, or 6. There are 6 outcomes. But here, in this little spread here, we're talking about a distribution of probabilities for all possible amounts of 3s that could come up. So there really are 2 outcomes here in this situation. Either I get a 3 or I don't get a 3. That's what we're talking about for binomial. So what's the probability you roll no 3s? Well, I could set up a fraction for each die, couldn't I? Non-3s. There are 5 non-3s in all the options you could get when you roll a die, so 5 out of 6. Couldn't I do that 5 times? So 5 out of 6, 5 out of 6 for the 3rd die, the 4th die, and the 5th die? And that should be 5 out of 6. And then I'll just type it in as 5/6 to the 5th power, right? Should be my probability. So the probability I get no 3s when I'm rolling 5 dice is going to be, let's round nearest thousandth. So we'll say 0.402 when rounded. All right, moving on up. What's the probability? You're still rolling 5 dice. And what's the probability you get 1 3? Well, let me think of how I might set this one up before I commit to a final strategy. Let's say I get a 3 and it comes first. So that's a 1 in 6 chance that that's going to happen. Now, exactly 1 3, wouldn't that mean all the rest of the dice come up as non-3s? Because that's what it should mean. So then shouldn't there be 4 more fractions of 5 6? I want you to take a look at this. See if you can find any mistake in what I wrote or see how comfortable you feel with using this strategy. So if I multiply 1 6 for the 1 3 times 4 5 6 for all the other non-3s, is that enough to put? Well, actually it's not. I should think about it. This isn't just the one outcome that could happen. Couldn't the 1 3 come first, second, third, fourth, fifth? Right? It could come in any of those slots. So here's how we're going to amend this. This is a good strategy as long as I take it all and I multiply it by the 5 ways in which I could get the 1 3. It could come in each of those 5 slots. So the 5 times this whole thing. And I have a disclaimer for you. We are actually going to get an easier method to do these questions by the end of the lesson, so don't fret, but this is one good way to do number 2. I'm going to multiply this. This actually gives me the same exact solution as the last one, coincidentally, because of the 5 that you're putting out front. Check it with the calculator, you get 0.402 again. Okay, so 2 down. Now let's move up the ranks. 2 3s. Okay, well, I gotta think for a second. This one's a bit more complicated. 2 3s, let me first do the part that I did in blue above, and I'll leave a little space just in case, like in the last one, I have to multiply something out front. So wouldn't it be, okay, let's say we get a 3 in the first slot, and we need 2 of them, so a 3 in the second slot, and then we follow this with 3 non-3s? Does that look good for the fractions? 2 3s and then 3 non-3s. Now I got to think of how many ways that could happen. Well, we've come full circle in the unit, right? How many ways can you pick 2 of 5 dice to be 3s? And that's a combination. The order doesn't matter here. It's going to be 5 total dice, C2. That's what makes this a little bit more complicated. I'm going to circle this part to it too. It's 5C2, the ways you can cycle 2 3s through those 5 dice times those 5 fractions. Just for the fun of it, I'll go back in and find a combination again. And I want a 5C2. So I'll go 5. I got to find combinations in the math probability menu. And I see it in slot 3 there, 5C2. I want to multiply that by 1/6 twice, so I'll go 1/6 in shorthand to the second power, times 5/6, and we'll raise that to the third power. So times 5/6 to the third, we'll round this to the nearest thousandth to get about 0.161. Okay, now I'm hoping we're starting to see a pattern here. I want to write the strategy for number 4 definitely in shorthand here. It says probability of getting 3 3s. Well, I'd have a bit to do. First, I'll write the combination. You have 5 dice. How many ways can you choose 3 of them to be a 3? And then you've got the fractions. 1/6, the 3's to the third power because I want 3 of them. And then 5/6 to the second power. The other 2 I want to be non-3s. Here's your shorthand that we discovered. So you get, if you type that in, a 0.032 rounded to the nearest thousandth, right? Our probabilities are getting a bit lower. 4 3s is going to be pretty rare. 5C4, you want 1/6 to the fourth power following the pattern. 5/6 to the first power, and look how tiny this is, 0.00 when rounded, 3-2. Went out a little bit further for that one. 5 3s. In one of my favorite dice games, they call this Yahtzee, right? You roll 5 dice, they all come up on 3s. There's only one way for that to happen. 5C5 actually equals 1, and then times 1/6 to the fifth power. You don't have any non-3s, so the 5/6 to the 0 power doesn't even need to be present. And you get the tiniest of probabilities, 0.00013. Now, just as a point of interest, if I took these circled values and wrote them and made a table out of them, basically, it's called a probability distribution. It's a list of all the probabilities for all possible cases, all possible amounts of 3s from 0 up to 5. And guess what would happen if I added up, if I took the sum of all those probabilities? Well, if I added them up, they're all total cases, I'll get what happens 100% of the time. If I added up all those numbers, albeit that they're rounded, I should get 1. Okay, let's move on. Now let's summarize what we just figured out before I promise we're going to get to that shortcut. It says for a binomial probability distribution, there are a fixed number of trials. Did that happen in the last situation? Well, yeah, I'm only rolling 5 dice. There's a fixed number of times I'm going to try to get a 3. The trials are independent of one another. You'll remember from our probability unit that independent trials, the probability of one event happening has no effect on any of the other trials, right? When I roll a die, I still have a 1 in 6 chance of getting a 3 throughout the experiment. Each trial has 2. That's where the binomial comes from. 2 possible outcomes. I put some examples here. You succeed or you fail. You could say succeeding is getting a 3, failing is not getting a 3 when you roll a die. Hitting a target or missing a target. You could flip a coin and get heads or tails. That's 2 outcomes. You could plan on having kids and there could be a boy or a girl. So possible outcomes is going to be 2. Suppose, now let's put some variables to this. Suppose you have n repeated trials, each with probability of success we'll call P. And I wonder if you've heard of the phrase mind your P's and Q's, because we use Q for the other letter. We're going to say probability of failure is going to be Q. And P plus Q adds up to 1, kind of like all those numbers in that distribution above added up to 1, because either you're going to, on one trial, you're going to succeed or you're going to fail, right? There's no other option, I hope. So the 2 probabilities should add up to 1. We'll talk more about that in a little bit too. Then the binomial probability is, this should be, as crazy as it looks, should be recognizable from what we just did. It's your total number of trials, 5 dice, choose how many you want to come up 3s. So NCR, we'll say there. And then probability of, oh, you know what? It would be X here. That's a typo. So NCX, how many you want to come up as 3s, if you want to change that. And then it's probability of success to the X power. If I want, let's say 4 3s, X is 4, I would raise 1/6 to the 4th power. And then probability of failure to the N minus X to the 5 minus 4. I'm so pumped to get to this shortcut that, yeah, I'll use this formula to do number 7, but then have your calculator handy after that. So it says we have, let's look at these examples. Section 1 on the SATs has 25 multiple choice questions. There are 5 answer choices per question. Find the probability of each outcome. Do you consider this situation to be binomial? And I hope so. It's binomial because either you're going to get a question right or you're going to get a question wrong, right? There's 5 answer choices per question. So let's actually, I'll bring this out here so I can say n is your number of trials in this situation. So you have 25 trials. You're trying to get the answer right on 25 questions and you're doing something crazy. You haven't studied. You know nothing about these answers. You're just going in as blind guesses. Do not recommend this on the SATs. What's your probability of just blindly guessing one answer correct? We'll call that P, probability of success. Well, you have a 1 in 5 chance, right? One of those answers is correct out of 5. That should be able to get Q for you as well. Don't you have a bigger chance of guessing the incorrect answer? Well, yeah, the other 4 choices out of 5 are going to be failure. I'll use decimals for these. I'll say 0.2 for P, and then I'll say 0.8 is going to be Q. And you'll see us using those throughout these examples. What's the probability you go in and guess and you get exactly 15 correct? Okay, so here goes. Using the formula, it's NPX first. So N is 25. How many ways can you get 15 correct out of 25? So start with that combination using the formula. Probability of success, 0.2, we want to get 15 of them exactly correct. Probability of failure, right? We want the others to be wrong for some reason in this case. And it'd be 25 minus 15 to the 10th power. If you take your time, feel free to pause the video, type this into the calculator, round to the nearest thousandth, so we agree on an answer here, and see if you get a 1.15 times 10 to the negative 5th power. So you've got roughly 0.00015 of a chance. Very low odds you're going to get exactly 15 correct. All right, I feel like this is taking too long, and we've got this calculator. Let's use it to our advantage. So you're going to see some shortcuts at the bottom of the page, and I'm going to show you some new notation here for another way you can more quickly get that same answer. Okay, so here goes. This is a binomial probability distribution, so I want you to write the word. I'll say equals BINOM, binom PDF. That acronym is for probability distribution function at this point. It gives you the probability of exactly one case of successes occurring in a binomial experiment. You're always going to put N, comma, P, comma, X here. And this is what I mean. N is your number of trials. And we said N in this case are the number of questions you're trying. So 25 questions. P, I'm going to use a comma here, and there's actually a comma on the calculator that I can show you. P is the probability of success, so I'll put a 0.2 here with a comma. X is your amount of successes that's desired. In this case of number 7, I'm desiring for 15 to be correct. And this should point to that same exact solution. Let's find all of this on the calculator. So can you find distribution here? It's hiding a little bit. It's second and the variables key, the vars key that's over by clear, where you see DISTR. And you have to scroll down pretty far. Past the numbers here, a bunch of statistical things that we see until, ooh, I found it. If you look at what we're going to use today are letters A and B in the second in distribution menu. And let's type in Binompdf. So I'll hit enter for Binompdf. Then your calculator either has this interface or it's just asking you for these 3 numbers. 25, comma, 0.2, comma, 15, and the comma key is right up here by the parentheses that we can use. Mine says number of trials. Let's type in 25. I'll hit enter. Probability of success, they call it P, is going to be 0.2. X value, how many successes you want, is going to be 15. A little enter. I see the format of it, how anybody would type it in with the comma keys, hit enter, and bam, we get the same exact solution. So from here on out, you have the choice of how you want to show this work, but I actually prefer this notation. This blue and black here can be the work that you show, and you can round your answer for me there so that you actually, let me put this all in parentheses, you don't have to show all this. This stuff in red is not going to be necessary if we can just use the calculator to our advantage. Can we try a second one? Let's try 8 the new way. Probability of getting exactly 3 correct. Let's use a Binompdf. So here's the work I would show. Binompdf, since I got to know what you're typing into the calculator. 25 trials, probability of success is still 0.2. I want to get exactly 3, a lot fewer correct on this one. So I'll do the same thing. Second distribution. I want to scroll down to Binompdf, so letter A. And then let's use 25 still as the number of trials, 0.2 as the probability of success, but we're changing the desired successes to just 3 right answers. I really hope that doesn't happen on the SATs, but you have a stronger chance of this happening. A 0.136 when rounded. Okay, so that's for one case of exactly a certain number of successes. Stay tuned for the next part of this where we go over the other examples. See you soon.